We were solving the problems on Green's theorem. We'll continue. The next problem is verify Green's theorem for integral over C xy plus y squared into dx plus x square dy, where C is closed region between y equals to x, y equals to x square. So now we need to first identify the common points on both the curves, that's points of intersection. Just before going for the point of intersection, we basically need to look at what type of curve we are talking about. So one of the curve is y equals to x square, that's a parabola. Okay, it is a parabolic curve like this. Okay, since we need only on one side, let's draw it only on that side. Okay, and the second is a second curve, y equal to x is a straight line. Okay, so there are 2 points of intersection. We are one this and second one is this. All right, so now let's try to find the point of intersection. Y equal to x and y equal to x square. Sorry, so this is y is first y is x, second y is x square. X equal to x square we are going to write as per the definition. So this implies x square minus x equal to 0. So x into x minus 1 becomes equal to 0. So this implies either x is 0 or x is x minus 1. When we equate to 0, x becomes equal to plus 1. So when x is 0, y is equal to x, so y is also 0 or y is 1. So we have 2 points where the intersection happens. One is this and another one is this. Right, so these are the 2 points of intersection which we can see on the graph, and let's call this is O, origin a, that is 0 comma 0, and the second one is this is a point A which is 1 comma 1. Let's say this is the path in which we travel from O to A and A to back O to complete the closed path. Now in the next step, our intention is that we have to apply the Green's theorem. So as per the Green's theorem, the integration of over the region C, the given m dx plus n dy, this has to be shown equal to integration over the region R. This is dou n by dou x minus dou m by dou y dx dy. All right, now to start with the LHS, that is, I want to perform integration over C. This is m dx plus n dy. According to this problem, this is nothing but integral over C. This is xy plus y square into dx plus x square dy. So looking at the curve, I know that I have two options to travel from O to A, but we choose the one which is on the y equal to x square curve first. So using y equal to x square, we reach from 0 to that is 0 0 to 1 1, right? So let's also mark some more details about this, the points, right? So we know that this point should be this is 1 comma 0, and the other point should be 0 comma 1. So these are the points. We use them to identify, right, the range of x or y. So this straight line is y equal to x line, and the green colored curve is the curve that is y equals to x square. All right. So we know that we are going to consider two different sections of, or two different curves to move from O to A once and A to O back. So along the first half, let's do the integration. That is along OA, right? So along OA, when I move from O to A, this is y becomes equal to x square. This means wherever you have a dy, you can write 2x dx, right? And when I move like in that range, I am writing in terms of x now. I'm replacing y in terms of x. So I look for what is the range of x there. So this is 0 less than or equal to x less than or equal to 1. So 0 to 1 is my limit now, right? This implies integral over C. I can write OA, integral over OA. This is xy plus y square dx plus x square dy can be replaced as integration x is equal to 0 to 1. I'm replacing every y by x square. So this is x into x square. So this is x cube plus y square. Y is x square. So this is x square square. So this is x to the 4. X cube plus x to the 4 into dx plus there is x square, it is as it is, x square into dy becomes 2x dx. So this is the formula to be used in order to simplify, right? So this is x is 0 to 1. We have there is a x cube and another x cube coming from the last term, that is x square into 2x. So there is a 2x cube. 2x cube plus this x cube makes it 3x cube, plus there is only one term for x to the 4. This is dx. So we have to solve only one term now. So this is 3 times, this is x to the 4 by 4. X cube becomes x to the 4 by 4 after integration, plus x to the 4 becomes x to the 5 by 5. This whole term I need to replace with the limits 0 and 1. So we know that this is 3 by 4 as the first term, and the second term is 1 by 5. So this becomes 19 divided by 20. Okay, that is along OA. Now we have to come back to A from O using the other path. So we'll write uh, along say AO. So now we are using y equal to x line. This implies every dy can be equated to dx, right? And once again, now in this case, x varies from 1 to 0. So x begins with 1, right? So we start with x 1 greater than or equal to x greater than or equal to 0. It's 1 to 0, right? So now we'll write the integration. This implies integral over AO, the same term, that is xy plus y squared into dx plus x squared dy. This term becomes equal to, we have integration x starting from 1 till 0. So y is also x. So this is, first term is x squared plus the second term is anyway y, so x squared. There is a dx plus x square dx. So we have integration 0 to 1 for x, x square, x square, x square. So there are totally three terms of x square. So this is 3x square dx. To simplify this, this is 3 times x cube by 3 from, sorry, I put the limits wrong in the previous step, so please correct that. This should be 1 to 0. So this is starting from 1 to 0. So same thing copies here, 1 to 0. So this is equal to 1, 3 cancel. So 0 minus, this is 1 cube, so 1. So this is minus 1. So previous answer is 19 by 20 and the present answer is minus 1. This implies the LHS is equal to 19 by 20 minus 1. So this is minus 1 by 20 is the LHS. Now we need to evaluate the right hand side of the equation and we should justify that we are going to get the same answer as per the Green's theorem. So next part, we denote m value. M is equal to x y plus y square and n is equal to x square. This is given in the equation, right? So I need dou m by dou y. With respect to y, we are differentiating. So dou m by dou y is equal to x plus 2y. Dou n by dou x is equals to 2x. Right. Now we need the term that should be used in integration on the right hand side is dou n by dou x minus dou m by dou y. So this is 2x minus x plus 2y, right? So I can reduce this to 2x minus x is x minus 2y. This should be used in the integration. So first, let us recall, we need to find the R, which is the region bounded between the two curves, y equal to x square and y equal to x. All right, so let's do that. So start with the RHS term. This is double integration over the given region R. This is dou n by dou x minus dou m by dou y into dx dy. So let's write this. So this is equal to, first I need to decide the regions for x and for y, right? So as I move from left to right, that's the limit for x. X starts from 0 and goes till 1, right? When I move along the curve in this, x varies from in this whole region. So we are talking about this whole region. So within this region, what is the range for x? So range of x is straightforward, right? Range of x is x start from 0 and goes till 1. So let's write that now. So x is equal to 0 to 1, right? Within this range, right, we have to give a range for y that exactly, right, talks about the region of our interest. That is only this much. You see that y actually varies between the two curves in any point, between any 2 points on the curve, right, on the two regions. The range of y is always decided, right, by this particular black colored small strip which we can consider. Okay, this is so the bottom of this particular strip touches the y equal to x square. Minimum value is on that curve and maximum value lies on the top curve, that is y equal to x. So you can see that y starts from x square and goes till the y equal to x curve. So limit for the y is straightforward now. So y starts from x square and y goes till the top, that is y equal to x. So the limits of y should be written as y is x square and going till x. Write the function dou n by dou x minus dou m by dou y, that is x minus 2y. So dx, this is dy dx. So dy comes first because inner integration is all about y and the outer integration is about x. So this is integral x is equal to 0 to 1. Let us integrate the inner term. So x becomes xy minus 2 times y square by 2 should be substituted as x square till x, then needs to be differentiated with respect to x. Okay, so this is equal to integral x is equal to 0 to 1. When I substitute x over there, right, the terms become x square minus x square. This is the first substitution. Y becomes equal to x over there minus. Next, every y I am substituting as x square. So x square comes into the first term. X into x square is x cube minus y square. So y is a x square. So x square square is x to the power 4. Right. This whole term now needs to be simplified and integrated with respect to x. So the first term is, anyway, it's 0. So this is equal to, I write a simplified version before I integrate. So this is x to the 4 minus x to the 3 into dx. So negative I'll take inside the bracket. So this means it is, okay, now we can directly integrate. So x to the 4 becomes x to the 5 by 5 minus this is x to the 4 by 4 starting from 0 till 1. So this is 1 by 5 minus 1 by 4. So 4 into 5 is 20 in the denominator. So 4 goes to left, 5 comes here. 4 minus 5 is minus 1 by 20. So you can see that this LHS is equal to RHS, and that is the solution of this problem. Next problem. Verify the Green's theorem for the function integral over c, that is x squared plus y squared dx plus 3 times x square y dy. Okay, where c is the circle x square plus y square equal to 4, right? Now, so we'll start with the left hand side of the Green's theorem. So equation first, let us write the equation of Green's theorem first, which we need to prove. So integration over c, this is m dx plus n dy is equal to double integration over the region R. This is dou n by dou x minus dou m by dou y dx dy. So first we'll start with the left hand side. Therefore LHS, this is integral over this c, this is x square plus y square into dx plus 3 times x square y dy. Right. So what we do here, whenever I want to discuss about a single circle, we always prefer to shift into the r comma theta format, where r is the radius, theta is the angle, and that coordinate system is called as the polar curves. So to convert a xy curve, that is in the rectangular format, to the polar format, we have to use the following notation, right? So first let's go for this. It says that x square plus y square is equal to r square. When you compare with this, the given equation x square plus y square is equal to 4, this implies the radius of the curve is expected circle is 2, right? So we put x is equal to r cos theta, so that is equal to 2 times cos theta, and y is equal to r sine theta, so this is equal to 2 sine theta, right? For a circle, theta varies from, theta is between 0 and 2 pi. All right, so the between the curve, whenever we are trying to integrate, we are doing this. So r is the function x and y both are written in terms of, right, theta, so we can definitely use this directly, and the integration should happen with respect to theta, right? R has been fixed to 2, so we don't have to worry about it. So this is, therefore the left hand side becomes equal to, now integration, this is theta varying from 0 to 2 pi, theta is 0 to 2 pi. So let us write the term x square plus y square into dx. So what is x square plus y square? It's actually 4, right? So we can write 4 into dx should be replaced by, right? If you differentiate x with respect to theta, this is, right, cos theta differentiation is minus sin theta. There is a 2. So minus 2 into sin theta d theta. That's the first term. Then plus, once again, integration theta is equal to 0 to 2 pi. So look at the function. It says that 3x squared. So there is 3 x square. X is 2. So 2 square 4 into x is cos theta. So I have cos square theta. 3 into 4 cos square theta into y is 2 sin theta into there is a dy. Dy should be written as, right, 2 into y is actually a sine function. Differentiation of sine is a cos, right? Cos theta d theta. So we need to simplify this equation to get the answer. So this is 4 into 4 into 2 is minus 8, and we can integrate. When we integrate sine theta, you get minus cos theta. So this is into minus cos theta from 0 to 2 pi. So this minus and minus will cancel out. Then we have plus, let's do the integration. Integration from theta is 0 to 2 pi. 4 into 3 into 2 into 2. This is 48. Cos square into cos, it's cos cube theta into sine theta d theta. So second integration is also straightforward now. This is equal to, so cos theta, cos of 2 pi, right, is 1 minus cos 0. So cos 0 minus cos 0, this term is gone. First term is, we can directly cancel this. So this is 0 plus 48 times. So cos cube theta, and differentiation of cos theta is with that. So I can directly write this as cos to the 4 theta by 4. Substituting 0 to 2. So you can see that this is first term is anyway 0. I'm not going to write once again. So this is 12 times cos to the 4 theta. So cos 2 pi is 1. 1 to the power 4 is 1 minus cos 0 is also 1. 1 to the 4 is 1. So the answer becomes equal to 0. This is the LHS. Okay, then let's move on to the right hand side equation now. So RHS term to be evaluated is double integration over a given region R. This is dou n by dou x minus dou m by dou y into this is dx dy. So for a given function, the m was equal to x square plus y square, right, and n was 3 into x square. So this means the dou m by dou y, dou m by dou y is equal to differentiation. This is 2y, m with respect to y, and dou n by dou x is 6x. Okay, sorry, there is a 3x square y, so this becomes equal to 6xy. All right, now, so this implies the right hand side now becomes equal to I have to write the double integrations, but I'll decide the values of x and y first. I'll write what is happening to x and what's happening with the y. Okay, so I can see that in this given curve, which is a circle, right? In the given circle, uh, x actually varies from the leftmost point, which is at -2, to the rightmost point, which is +2. Right. Now, in order to substitute the value of the y, let's look at the equation. So, x squared plus y squared is equal to 4. So, if you want to decide what happens to with y, so take x to the other side, 4 minus x squared. So, y should be equal to plus or minus root of 4 minus x squared. So, y's minimum value will be minus of root of 4 minus x squared, and the maximum value is root of 4. This is 4 minus x squared. So we identified the limits of our integrations for both x and y into uh, the dou n by dou x minus dou m by dou y should be this is 6xy minus 2y into dx. First integration happens with respect to y, that's why I need to change this as dy dx. Okay, this part is just for your reference. Now I think we can take a 2y common from that. Okay, because x and y can be separated here, so we'll write another step here. This is x is -2 to +2 and y is minus of root of 4 minus x square till root of 4 minus x square. Let's take the 2y common. This is 3x minus 1 into dy dx. So 2y, let us integrate now. This is equal to integral x is -2 to +2. There is 3x plus 1, which is a function of x. Now I do the with respect to the function of y. 2 into y becomes y square by 2, and a substitution happens. This is minus 4 minus x square to plus 4 minus x square into dx. So 2 will cancel. So this is equal to integral, that is x is equal to -2 to +2, 3x plus 1 into, so y whole square. So first term should be 4 minus x square. After substitution, the y as this number, y square is this, minus, so y is minus of this, but square becomes equal to same, right? So 4 minus x square into dx. Now you see that this term cancels, the whole integral is 0. So whatever, 3x plus 1 into 0 is whole thing 0, integration of 0 is a 0. See, we got 0, this itself is the, we started with the RHS, so we are equating this with the LHS now. This is equal to LHS equals to RHS. So hence we proved this. Green's theorem is proved. Now let us go to the next question. This is so the next question is like this. show that the area enclosed by a plane curve C is half integral over C x dy minus y dx. Hence, find the area of ellipse x square by a square plus y square by b square is equal to 1. Okay, now we need to find the required area. Right, first we need to show that the area is given by a specific function, right? Let's do that. So let's write, so the equation for Green's theorem, it states that integral over C m dx plus n dy should be equal to double integral over a region R. This is dou n by dou x minus dou m by dou y into this is dx dy. Okay, so to make this point clear, so let's write the equation that needs to be used to calculate the area of any given curve, right? So also the area enclosed by a curve, let's say that area A is given by double integral over the region of its existence dx dy. All right, now let us try to calculate the substitution for the above equation by using, say, let's take n is x by 2, right, and m is equal to y by 2. If we take this and perform the dou n by dou x minus dou m by dou y, so dou n by dou x will be half minus dou m by dou y. If I write like, okay, let's put a minus over there, m is minus y by 2, this becomes once again a minus half, so that the dou n by dou x and dou m by dou y becomes equal to 1. So this implies, now let us substitute in the Green's theorem itself. This implies Green's theorem becomes equal to, left hand side you see that is m dx plus n dy. M and n are, right, first function is y and second function is x. All right, so this implies, now the left hand side is half integral over the given c, this is x dy minus y dx equal to, right hand side, this is double integral over r, right, dou n by dou x minus dou m by dou y is 1 dx into dy. This itself is the area which we had defined earlier. This implies the area, required area A is equal to half of integral over the C. This is x dy minus y into dx. So we will be using this as our reference to calculate the any required area here on this. So when only one curve is given and we are supposed to calculate its area, we should use this equation. Okay. Now in the same part they have mentioned about calculation of area of the ellipse, right? So let's write the ellipse first. Ellipse given is x square by a square plus y square by b square equals to 1. So when a curve is given, we should directly go ahead and substitute x is equal to a cos theta. A cos theta, right? This implies we need to substitute for dx. So dx is equal to minus a sine theta d theta. Okay, and we put y is b times sine theta. So this implies the dy is equal to b cos theta d theta. Right. So what is required area? Area A is equal to integral over the region C. It is x dy minus y dx. So now C, in the sense it has to be considered in terms of theta. So we know that theta varies from 0 to 2 pi on a plane. So this is equal to integral 0 to 2 pi for theta. Let's write x dy minus y dx. So x is equal to, this is a cos theta into dy is b cos theta d theta minus, this has to be y is equal to b sine theta into dx is minus a sine theta d theta. So this is equal to integration 0 to 2 pi. I can see that AB is common in both the terms, so I'll take AB outside. First term is cos square theta, second term is minus of minus plus sine square theta d theta. Alright, so this is now equals to, we can see that there is a cos square plus sine square theta which is equal to 1. It's simply AB. AB are constant, we'll take it out. So it's just theta starting from 0 to 2 pi. So one mistake, we missed the half at the outside, right? So there is a 1 by 2. A mistake, please correct. This is 1 by 2, 1 by 2 at the end. So there is a half. So this is half AB into 2 pi minus 0. So that is this. So this is the required area of the curve is pi into AB. So that's how we find the required answer.